Hello students, welcome back in this ROSE project. ROSE project is conducted by Raya Shikshan Sanstha's Sadguru Gadge Maharaj College Karad. Myself, Mr. Maske NP. I am here to teach you subject chemistry. My topic is topic number 4, that is chemical thermodynamics. In previous lecture, we completed concept of maximum work and pressure volume work and related numerical. Now in this lecture, lecture number 4, our first point is first law of thermodynamics. Okay, so statement here, energy can neither be created nor be destroyed, although it can be converted from one form into another. It means energy, we cannot create or cannot destroy energy, but we have to convert it one form into another form. That is chemical energy, it is converted into electrical energy. Then electrical energy also converted into chemical energy. Then kinetic energy is converted into potential energy. Potential energy is converted into mechanical energy. We can only convert energy, but we cannot create or cannot destroy energy. Okay, so this is the simple statement of first law of thermodynamics. Now, formulation of first law of thermodynamics. Suppose Q is the heat supplied to a system and W work done on the system by surrounding, then internal energy of system would be increases. So increase in internal energy, that is U of the system, is equal to sum of quantity of heat supplied to a system and amount of work done on the system. So we get change in internal energy, that is delta U is equal to Q plus W. This is our first formula for first law of thermodynamics. Okay, delta U means change in internal energy, Q means heat added to a system, and W means work done on the system. That's why sign of W is positive. Then change in internal energy, that is delta U, is the increase in internal energy of the system for infinitesimal changes. Infinitesimal means small changes. Okay, then it is formulated as change, it is denoted by small letter d. Du is equal to dq plus dw, or simply we have to say delta u is equal to delta q plus delta w. Triangle, it is also called as delta, but after completion of reaction, triangle, that is delta, is used, and infinitesimal change, that is small change, for that purpose small d is used. This is equation number 2. Now let us move to the problems on work done and pressure. Okay, so first of all we have to get problem number 4.4. 2 moles of an ideal gas are expanded isothermally and reversibly from 20 liter to 30 liter at 300 Kelvin. Calculate work done. Value of R is equal to 8.314 joule per Kelvin per mole. Then we have to use formula for maximum work, that is W max. W max is equal to minus 2.303 nRT log to the base 10 V2 upon V1. So we have to solve first given data. N is equal to 2 because 2 moles of an ideal gas. So value of number of moles, that is small n, is equal to 2. Temperature, that is 300 Kelvin is the temperature. V1 means initial volume of gas. So 20 liter is the initial volume. 20 liter to 30 liter isothermal and reversible expansion, that is final volume V2 is equal to 30 liter. Then value of R is equal to 8.314 joule per Kelvin per mole. Substitution of these quantities into the equation which gives W max is equal to minus 2.303 into N, that is 2 mole, into R 8.314 joule per Kelvin per mole, into 300, that is temperature in Kelvin, into log to the base 10 V2, that is 30 liter, divided by 20 liter. First of all, we have to solve this dividation, that is 30 divided by 20. So minus 2.303 into 2 into 8.314 joule into 300 log to the base 10 as it is 30 upon 20 is equal to 1.5. Then we have to find log to the base 10 1.5. So this step is remains as it is same, minus 2.303 into 2 into 8.314 joule into 300 into log to the base 10 1.5. So value is 0.1761. Then after solving this, we get our final answer, that is minus 2023 joule, and we have to convert it into kilojoule. So simply we can write it as minus 2.023 kilojoule. This is our problem number 4.4 or problem number first. Now next problem is 22 grams of carbon dioxide are compressed isothermally and reversibly at 298 Kelvin from initial pressure of 100 kilopascal when work obtained is 1.2 kilojoule. Find the final pressure. So we have to use formula for W max or W, that is in terms of pressure, minus 2.303 nRT log to the base 10 P1 divided by P2. Then first of all, we have to write correct given data for this numerical. P1 is equal to 100 kilopascal, that is initial pressure. Initial pressure is 100 kilopascal. Then W, work obtained is, that is W is equal to 1.2 kilojoule, that is we have to convert it into joule. So 1 kilojoule means 1200 joule. Okay, then we have to find value of R is already we have to know, 8.314 joule per Kelvin per mole. So we have to find number of moles. So number of moles we have used 11 standard formula, that is W divided by M. W means given mass, M means molecular mass. So 22 gram is the given mass of substance divided by molecular mass. M means molecular mass. So molecular mass of carbon dioxide is 44. So 22 gram divided by 44 gram per mole is equal to 0.5 mole, and temperature of this reaction is 298 Kelvin. Then hence 1200 joule, that is 1200 joule, is equal to minus 2.303. The value of W is 1200, that is 1200 joule, is equal to minus 2.303 into N, that is 0.5 mole, into R, that is 8.31 joule per Kelvin per mole, into T, that is 298 Kelvin, into log to the base 10 100 kilopascal divided by P2, that is final pressure. Okay, or log to the base 10, we have to shift this term to the left hand side, then we get log to the base 10 100 kilopascal divided by P2 is equal to minus 1200 divided by 2.303 into 0.5 into 8.314 into 298. After solving this term, we get value of minus 0.4206. Then log to the base 10 kPa, 100 kPa divided by P2 is equal to antilog of minus 0.4206 is equal to 0.3797. Therefore P2 is equal to 100 kilopascal divided by 0.3797 is equal to 263.4 kilopascal. That is our final answer. So final pressure is P2 is equal to 263.4 kilopascal. This is numerical number 2. Then our next point is first law of thermodynamics for various processes. Now, number 1 is isothermal process. We have already know iso means constant and therma means heat or heat associated with temperature, means constant temperature. The process in which temperature of the system remains constant. Now, so as temperature of the system is constant, internal energy, that is delta U, is also constant. That is delta U is equal to 0. So what is the formula of first law of thermodynamics? That is delta U is equal to Q plus W. So delta U, value of delta U is equal to 0. Then for isothermal process, value of delta is equal to 0. We have to put this 0 into first law of thermodynamics, that is delta U is equal to Q plus W. So W is equal to, final answer, W is equal to minus Q. That is the first process in isothermal process. Now, second process is adiabatic process. We have already know in adiabatic process, no exchange of heat between system and its surrounding. That is symbol of heat is Q. Q is equal to 0. So, Q is equal to 0. Then we have to put this value 0 in first law of thermodynamics formula, that is delta U is equal to Q plus W. So we get final answer minus delta U is equal to minus W. So this is the second process called as adiabatic process. Now third process is isochoric process. We have already know iso means constant or same. Course means volume. The process which takes place in constant volume called as isochoric process. So equation of first law of thermodynamics, we have already know delta U is equal to Q plus W. Then substitute value of W. W is equal to PEX minus PEX into delta V. This is the formula for pressure volume work. So we have to substitute the formula of work into first law of thermodynamics formula. So we get delta U is equal to Q plus minus PEX into delta V. So in isochoric process, we get our final equation delta U is equal to Q minus PEX into delta V. But in isochoric process which takes place at constant volume, so delta U is equal to QV because volume is constant. Volume is constant. In isochoric process, volume is constant. So as volume constant, no expansion and no compression there. So delta is equal to QV. V indicate subscript. Subscript indicate at constant volume. So change in internal energy, that is delta U is equal to Q into V or QV. V means subscript and meaning of subscript is at constant volume. Okay, so this is process number 3. Now let us start process number 4, isobaric process. Iso means constant, bars means pressure, the process which takes place at constant pressure called as isobaric process. Now in such a reaction, delta V is not equal to 0 because pressure is constant. But in such a reaction, change in volume is not equal to 0. So replace Q by QP in isochoric process. Replace Q here by QP in isochoric process. So we get and rearrange the formula. We get the final equation, that is QP is equal to delta U plus PEX into delta V. That is the final formula for isobaric process. QP is equal to delta U plus PEX into delta V. Now, this reaction is carried out in only open condition under constant pressure. So in isobaric process, or we have to get this formula, so reaction will be carried out in open condition. Now, next point is enthalpy. enthalpy. So here is the definition. Enthalpy is sum of internal energy of system and energy equivalent to pressure volume type of work. We have already derived the concept of PV type of work as expansion energy is lost and compression energy is gained. So that energy is PV type of energy. And enthalpy is the sum of internal energy and PV type of energy. So formula of enthalpy, symbol of enthalpy is H. So sum of internal energies, symbol of internal energy is U, and PV type of energy, so plus P into V. PV type of energy means, I am telling you once again, in expansion energy is lost and in compression energy is gained. So that energy is called as PV type of energy. Energy for expansion and compression in pressure volume type of work. So change in enthalpy, that is delta H, is also state function, is given by delta H is equal to H2 minus H1, that is equation number 2, where H1 and H2 is the enthalpies of initial and final state. H1 is the enthalpy of initial state and H2 is the enthalpy of final state. From equation number 1, we can write here H1 is equal to U1 plus P1 and V1. Initial state having value H1 is equal to U1 plus P1 V1 and H2 is equal to U2 plus P2 into V2. So after that, change in enthalpy, that is delta H is equal to U2 plus P2 V2 minus U1 plus P1 V1. So we have to rearrange U2 minus U1, that is U2 minus U1, I am writing here in bracket, plus sign as it is, P2 V2 minus P1 V1, P2 V2 minus P1 V1. So U2 minus U1 is equal to delta U plus delta V2 minus V1 is equal to delta V, and P2 minus P1 is equal to delta P. So I am here as simply written is as delta in bracket PV. So at constant pressure, P1 and P2 is equal to P, then delta H is equal to delta U plus P into delta V, that is the equation number 4. So if the pressure inside and outside is same, or external pressure, that is PEX is equal to P, gives isobaric process. So QP is equal to delta H is equal to QP. So QP is equal to delta U plus P delta V. I am writing here in simple way from equation 4 and equation 5. QP is equal to delta H. Delta H is equal to QP because pressure is inside and outside is same, that is internal pressure and external pressure is same. So delta H is equal to QP. So I am writing here delta H is equal to QP, that is equation number 6. It is equal to the change in heat transferred at constant pressure. Both enthalpy, that is symbol of enthalpy is H, and QP is the state function. QP is the state function. Then next point is relationship between enthalpy change, that is delta H, and internal energy change, that is delta U for the chemical reaction. So in the equation of enthalpy related as delta H is equal to delta U plus P into delta V, that is the definition or concept of enthalpy. The relationship between delta H and delta U, these are the two conditions are there. Number first, in reaction involving reactant and product exist in solid and liquid phase, so change in volume is very small, so delta H is equal to delta U. It means if we use reactant and product in physical state, that is solid and liquid, so in that case delta H is equal to delta U. Now second, For the reaction involving gases, so delta V can't neglect it. So delta H is equal to delta U plus P delta V. Delta U as it is plus P into V2 minus V1, that is delta U PV2 minus PV1. So if reaction involving reactant and product are exist in gases, so delta V we can't neglect. So we get the equation number first, where V1 is the volume of gas phase reactant, V2 is the volume of gas phase product. Applying ideal gas equation, that is PV is equal to nRT, where N1 moles of the gas reactant produce N2 moles of gaseous product. Then equation is PV1 is equal to N1 RT and PV2 is equal to N2 RT. That is equation number 2. Substitute equation 2 into equation 1. We get delta H is equal to delta U plus N2 RT minus N1 RT. So delta U plus N2 minus N1 RT is the common. So delta U N2 minus N1 is equal to delta Ng, G for gaseous phase reactant and product. So final equation is delta H is equal to delta U plus delta Ng RT. That is equation number 3. This is the relationship between delta H and delta U. Delta Ng is the difference between number of moles of gaseous product and gaseous reactant. Okay. Now problems on delta H and delta U. So problem number 4.7, delta H for the reaction, twice of carbon plus thrice of hydrogen gas, which gives C2H6 gas, is minus 84.4 kilojoule at 25 degrees Celsius. Calculate change in internal energy for the reaction at 25 degrees Celsius. Value of R is equal to 8.314 joule per Kelvin per mole. So formula is relationship between delta H and delta U. Delta H is equal to delta U plus delta Ng into RT. Delta Ng means moles of product gases minus moles of reactant gases. So delta Ng is equal to, we have to only use reactant and product in gaseous phase. We can't use reactant and product in solid phase. So delta Ng is equal to moles of product, that is stoichiometric coefficient of C2H6 is 1 in existing gaseous phase. So I am writing here 1 minus reactant, where hydrogen is gas. So we have only used stoichiometric coefficient of hydrogen is 3. We can't use 2C, or stoichiometric coefficient of carbon is 2 because carbon exists in solid phase. Solid phase and liquid phase, we have to neglect that. We have only used gaseous product and gaseous reactant. So 1 minus 3 is equal to minus 2 mole. So delta H is equal to delta U plus delta Ng RT. Delta H is equal to minus 84.4 joule. R is equal to 8.314 joule per Kelvin per mole. So we have to convert it joule per Kelvin per mole into kilojoule per Kelvin per mole. So we have to multiply by 10 to the power minus 3. So 8.314 into 10 to the power minus 3 kilojoule per Kelvin per mole. Substitution of this in above. So minus 84.4 kilojoule, that is the value of delta H, is equal to, we have to find delta U, calculate delta U, plus 8.314 into 10 to the power minus 3 kilojoule per Kelvin per mole into 298, that is the temperature of 25 degrees Celsius. We have to convert it into Kelvin. 273 plus 25, that is equal to 298 Kelvin, plus delta Ng is equal to minus 2 mole. So which gives delta U minus 4.96 kilojoule. So delta U is equal to, after solving this, we get value delta U minus 4.96 kilojoule. So final equation or final answer is delta U is equal to minus 84.4 kilojoule plus 4.96 kilojoule. So we get minus 79.44 kilojoule, minus 79.44 kilojoule. That is our answer. Okay. Now problem number 2 or 4.8 is, in a particular reaction 2 kilojoule of heat is released by the system and 6 kilojoule of work is done on the system. Determine delta H and delta U. Then according to first law of thermodynamics, what is the formula? Delta U is equal to Q plus W. So we have to use value of Q is equal to minus 2 kilojoule, because in a particular reaction 2 kilojoule of heat is released by the system, and by the system sign of Q is minus. So Q is equal to minus 2 kilojoule, and 6 kilojoule work is done on the system. Okay, so what is the value of work is done on the system? So W is equal to plus 6 kilojoule. Then we have put this value into formula first law. So delta U is equal to minus 2 kilojoule plus 6 kilojoule is equal to plus 4 kilojoule. So internal energy change having value plus 4 kilojoule. Then we have to find delta H. So we already know about delta H is equal to QP. Delta H is equal to QP. So delta H, what is the value of delta H? In a particular reaction 2 kilojoule heat is released. So delta H is equal to minus 2 kilojoule, or QP is equal to, symbol of it is Q. Q is equal to minus 2 kilojoule. QP is equal to delta H. Heat is released, that is delta H is equal to minus 2 kilojoule, because heat is released, that is Q is equal to minus 2 kilojoule. That is the numerical number 2. Okay. In this video lecture, we have completed some important point. Hopefully you have understood this. Thank you.